And another structure is same thing here. So carbon here, oxygen here, chlorine here. Let me see. Carbon, oxygen, chlorine. And then you have, and you have bromine like this. Yeah, that's the tools. Yeah, now that's the two. Yeah, so this is 1, 2, 3, and you can start to determine the chirality. So we need to view. We need to put our model so that our eyes, carbon and hydrogen is away from us. Is away from us. So this is up. Okay, this is up. This two up. And you can play with that. Let me see. Yeah, no, this is is not easy. We have bromine here, hydrogen, bromine. So let me see. So this one is not right because some black sphere can only have only 3 holes for each. So we cannot use that one. So this is correct. Okay. So this is carbon. This is carbon. And then this is bromine. Let me see. Red. Let's see. Bromine. Oxygen. Sorry, oxygen is green. Then we put oxygen green. So let's work on the first one first. Okay. First. We have this like this and chlorine red. And then bromine. And then hydrogen. Well, this bond is kind of weak. So we work on this first. You see, I have a green oxygen here, chlorine red here, and bromine here, and hydrogen is the white one, right? So can you get this one? Right? So this is outer plane. This is outer plane. This bromine is outer plane. Okay. And then we need to view so that our eyes, carbon and hydrogen are on the same line, and the hydrogen is away from us. So what did you get? You get this, right? Right? You see that? Here we got this. What I mean is that even though it's drawn like that, we know when you try to determine the chirality, this one is up. You see that? Here is green. Because why? Because these two bonds are bending down. So this can be confusing. If you're not familiar with this kind of configuration, you may say, oh, this is 1, 2, 3. You get what? You get S, right? You get S. But if you have this in your mind, you have this picture in your mind, these two bonds are bending down. And then if we view so that our eyes, carbon and hydrogen are in the same line, and the hydrogen is away from us, this bromine must be up, even though it's drawn down. It's drawn, you see that? That's the confusing part. So that's the reason I see when it comes to RS is, I can see, I mean, actually it's not fair because you, if you're not clear about this, if you don't have this picture in your mind, you will keep losing points. You see that? Even though it's drawing like that, but if you have this picture in mind, we know, oh, when we draw, you see bromine, you see green is here, oxygen is here, chlorine is here. And if we view so that our eyes, carbon, hydrogen on the same line, this bromine must be up. So that's the reason you see this one is what? 1, 2, 3. This one should be R. Even though we draw like that, we draw bromine here. Even though the bromine is drawn here, we need to know when you view the bromine is up. Why? Because these two bonds are bending down. The bromine must be up. Why? Because of this tetrahedral coordination. That's the confusing part. And then if you take a look at this one, and this hydrogen is up, this oxygen is up, this chlorine is here. And if we still want to put bromine, and you can see that here hydrogen is up, right? If we view this way. And then, so if we want to put bromine, still out of plane, we need to change these two. So we need to put the bromine here. Yeah, you see that? You see here, the hydrogen is still behind this plane, is on the other side. You see oxygen, chlorine. And then if we view so that our eyes, carbon, hydrogen are in the same line and the hydrogen is away from us, we need to view this way. And then for this one, this bromine is indeed here. This bromine is in here. And chlorine is here. So, and then oxygen is here. So it's what? S. So this bromine is indeed down, is indeed located at this down position. Why? Because of this tetrahedral shape. So this bromine is not here. When we draw this structure, the bromine is not here, but up. That's the confusing part. So we need to have this, tetrahedral configuration in our mind. We constantly need to refer to this. These two bonds are bending down. This bromine must be up. Okay. Any questions? Otherwise, yeah, we keep. So we need to have if you have this picture in your mind, when you determine the kinetic, you can never go wrong. We cannot draw based on this drawing. Based on this drawing, we cannot. So any questions? yeah, and then I will go through some difficult questions. So yes, yeah, we need to keep this tetrahedral coordination in our mind. Otherwise, when we determine the chirality, we can easily get wrong. So, yeah, I will send this website to you, and then you can, we can rotate and have this. Here, this database is limited. I cannot find the chiral. There's some chiral molecules. So first, you can see, well, here. So you can see that this is chiral carbon. This is chiral carbon. This is also you see the all chiral carbon. And in this case, if you look at each of them, it's not symmetrical structure, right? Because this is not OH group, so it's impossible. This structure cannot be symmetrical structure. So even though these are these S, they cannot cancel because they have different extent of chirality. They have different extent of R and S, so they cannot cancel. Only if this is OH, actually even this is OH is not even symmetrical. Okay. And then here you can see that at this stage, sometimes we don't have to find out the chirality. Sometimes we don't have to find out one by one. And then here you can just assume if this is R, right, then this must be S. And if this is R, this is R, right? They have the same, right? Therefore, is what? They cannot be enantiomers, right? Surely they have the same connectivity, but they are not enantiomers. Then it's diastereomers. And at this point, you don't need to spend time finding out the chirality. You can just assume, okay, if this is R, this must be S. If this is R, this must be R. Okay? So they are not mirror images of each other. And then, okay, maybe the easy way to do it. The second question asked, so which compound would have the lowest boiling point, right? Boiling point. And then from here we discuss if we're lowest boiling point. So this question is is quite straightforward. You see, for compound A, compound is alkane, right? Alkane. There's no hydrogen bonding. Compound B does not have hydrogen bonding either, but it has oxygen there. It has higher molecular weight. Therefore, compound B has higher boiling point than compound A. For compound C, D, E, all of them have what? Hydroxy group. And then when they have hydroxy group, they will have the hydrogen bonding. Okay, they have hydrogen bonding. Then compound C, question C, question 3, question 3. Then if you look at this one, and then we need to keep in mind for Fischer structures, okay, for Fischer structures, so question 3, for Fischer structures. Then when we draw like that, then it is what? We know by definition This is how Fisher structure is drawn. By definition, this OH group is like that. It's behind us. And then this hydrogen, there's a hydrogen here. Carbon hydrogen, right? So this is carbon, this is hydrogen. And then what? And then what? You see, if this hydrogen is down, this hydrogen is down, right? Then the other must be like that. And then up. Okay. And then we know when we want to determine the chirality, we always want to do what? We always want to make hydrogen away from us. So this here is hydroxide away from us. Then we do switch. Okay, we do switch. But we need to keep in mind when we switch two groups, the chirality also change. So we switch these two. Okay, we put the hydrogen behind and OH group here. So this is carbon. I will omit the other part. Okay. Then you can see. Okay, you see that these two bonds are up. Up. Right? These two bonds are up. Then when we view, so that hydrogen is away from us, we get what? We get this surely have the highest priority here. Then because this is up, this must be down. So 1 should be here, 2 should be here, and 3 here. This is what? This is R. We figure out this R, and we need to put it back. This must be S, because we do switch. We do switch. So that's, I prefer this way, you know, or maybe you have better three-dimensional feeling. You may, okay, hydrogen here. Then I can feel, I view from top, you know, you can do that. But I myself, I'm not very confident. So normally I do switch. See, this hydrogen is here, and you can imagine, okay, you can imagine you view from here, from top, right? From top, you can do that. But I'm not very confident. But you may have better feeling, three-dimensional feeling, and you can do that. I myself prefer this way. Hydrogen is not behind us. Now I switch. I switch this with another group that is behind us. And then once I switch, I figure out the chirality, then I switch back. So this must be S. You see that? S. So, and if, yeah, for the naming, should be B, because it's S. Yeah. So here, right? 1, 2, because we want to keep the minimum partition number for hydroxy group for the carbon that is attached to the hydroxy group, because hydroxy group has higher priority than triple bond. So this chirality, we need to practice, but we always need to have this picture in our mind, right? If you look at this one, because by definition, this is how we draw Fisher structure. The OH group is behind us, and these two groups are toward us. But we need to know whether this is really down. You know, you see that here, because these two bonds are bending down. Then when we view, this bromine is up. So that's the confusing part. Because I mean, this is how these 4 bonds are arranged, and we need to get familiar with that. Otherwise, you may make a mistake again and again in terms of the chirality. compound 4 is just naming. Question 4, question 5. Also naming. Okay, we'll skip that. So, question 6. So, let me see. Any question about this? It's kind of, the drawing, two-dimensional drawing of a three-dimensional structure can be very misleading. So we have to have this, tetrahedral coordination in our mind. Yeah. Otherwise, you can be easily misled by the drawing. The drawing shows the bromine is down, and then okay, bromine should be down. No, it's not. Because why? Because there are two bonds are down. Then this bromine must be up. When we view in a way that hydrogen is away from us. There's no way. You see that these two bonds. It's like that. But not like. Yeah, you see, when these two bonds are bending down, there's no way for this also to bending down. No way. We will view this way. We will view so that hydrogen is away from us. This hydrogen is away from us, right? Then we view these two bonds are bending down. Then this bromine must be up. No choice. This cannot be here. It must be up. So even though it's drawn down, but it's not. It's not. This is kind of very difficult. This hydrogen is away from us. These two bonds are bending down. Then the bromine must be up. This is very confusing. So question 6, which of the following could be used to synthesize 2-chlorine butane? So question 6. Butane. Surely A cannot, right? Because chlorine, for A, 2-chlorine will be added. Then B surely work. That's the way, to directly convert primary and secondary alcohol to primary and secondary chloride. So here is secondary. So B should work. What about C? C won't work, right? Because you will continue to react. You will continue to react. So D surely not work because 2 equivalent chlorine, 2 will be added to this triple bond. Okay, this seems very straightforward. Let's move on. Okay, question 7. Question 7. So we need to know the first step is not what? The first step only to replace hydroxide. Hydroxide group to chlorine group. So this part, there is no, this first step, no, or we can say retention of configuration. Retention of configuration. That means what we start from that, and then we get this methyl group. OH group, and then, right? In the first step, this will be replaced by what? Chlorine. So you pay attention. You see that? It's not drawn this way. It's not drawn this way. Why? Because this is down, then these two must be up. So there are so many details. When we pay attention, we need to pay attention. You see that? Because this is down, then these two must be up. Right? Because of this tetrahedral configuration, because of this tetrahedral arrangement. And then we know the second step. What? This is a secondary alcohol halide. Secondary, right? Here is chloride. Okay. And then this is very acetate. This is acetate. Is a good. So it's a good what? Nucleophile, because it's negative, right? Because it's negative, it's good nucleophile. So the second step will be what this reaction. So this is what? This is SN2 reaction. So and then this will replace that. When this occurs, it will be what? Conversion of configuration. Conversion of configuration. So it will the configuration will be converted. That means this group replace this group at the same time. The configuration change. So this one replace this one, and the configuration change. Then this group should jump here. Then we get the product what? A, the first one. So should be the answer should be A. The answer should be A. So any questions? Yeah, the first step, there's no configuration change.